After learning the definition for the complex integral of our function z along path c, at the same time with the properties of integral which we can use later on, let's talk about parameterizing the path. The question right now is, what does parameterizing the path mean? That's the question we need to address for this video. Take note that previously, the definition of the complex integral of your function f of z, any function f of z along your path c, smooth curve or the contour of c, is identified as this. The integral on the path is equivalent to, okay, the integral of your function of z of t, okay, times the derivative of your z of t with respect to t, and you will have your a to b, where a and b are actually your endpoints that you're going to consider later on along your path or curve c. The question right now here is this one here. What does this mean? Because we have f of z. Obviously, we have that function. Parameterizing the path means we can express each point of z on the curve in the complex plane as a function. Okay? That would mean we are going to use a different form of that in this manner. And this is how we parameterize the path. Okay? Say for example, our z, okay, let me use another color here. Okay? Our z is any complex number. We're going to take its equivalent of z of t, so that we can plug that in here and here. And take note, this z of t, a function of real variable t, is different from every function and in every path that you can think of. So there are different forms on parameterizing the path. Okay? This is actually, of course, we know that z is equivalent to your original function later on, before. This is a complex number x plus iy, right? This time, since we're going to parameterize that, this would be yield to x, okay, this is equal to plus iy of your t, any variable of t. But this t is in between a and b, the endpoints that you're going to consider here. Therefore, your z or z of t now would be expressed as x of t plus I of y of t. Your function, instead of having a certain function f of z that may or may not contain a imaginary unit I, but of course generally it should contain imaginary unit I, so is actually expressed now in this form, where your x would have a real variable t and your iy would also have that same variable t. Then with that now, we can now get the equivalent first derivative of that with respect to t, as we are going to plug in variables of t here. So basically, this is how we parameterize the path. If we're going to talk about it in simpler perspective, parameterizing mean you're giving your curve a speed and direction. They're telling you how to walk along it, not just where it is. So basically, your C is the path. You're giving it a certain magnitude or a certain value in terms of your real variable t, which you can plug in later on in your integral. So you'd actually solve for the integral of your function along that given path. As mentioned, we have different ways to parameterize the path C depending on your situation. We will be providing you with certain videos later on the equivalent parametric forms of your path along different situations. So please stay tuned in the next few videos. Thank you very much for watching.